A strange, rhythmic pulse echoed from deep space, a cosmic heartbeat with no obvious source. For years, it defied every explanation, even sparking whispers of an alien message. That is just one of 30 cosmic discoveries that took brilliant minds decades to unravel. By the end of this journey, you will understand how humanity's greatest scientific triumphs began as its most bewildering mysteries. We will uncover the true nature of ghostly signals that pointed to colliding stars and confront the invisible force that is tearing the fabric of the cosmos itself. What does it feel like to solve a puzzle the universe kept hidden for a generation? The first great cosmic mystery began with a line on a chart recorder. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a new radio telescope she had helped build. She noticed a faint, repeating signal, a pulse of radio waves arriving every 1.337 seconds with a precision rivaling the most accurate atomic clocks on Earth. The signal was so regular, so artificial in its perfect rhythm, that the team half-jokingly labeled it LGM1 for Little Green Men. Could this be a beacon from an alien civilization? The possibility, however remote, sent a thrill of both excitement and profound unease through the small research group. For months, they kept the discovery secret, quietly investigating while the weight of its implication hung in the air. The universe, it seemed, was tapping out a perfect, inexplicable code. The true explanation, when it finally came, was almost as strange as aliens. The pulses were not messages, but the lighthouse beams of a dead star. Theorists realized these signals could only come from a city-sized object spinning at a ferocious speed, a neutron star. These are the collapsed cores of massive suns that have exploded, crushed by gravity into a sphere so dense a single teaspoon of its material would weigh billions of tons. As this cosmic cinder spins, its immense magnetic field focuses beams of radiation that sweep across space. And if one of those beams points at Earth, we see a flash with every rotation. What Jocelyn Bell Burnell had found was not an alien signal, but a pulsar, a natural celestial metronome. This discovery did more than solve a puzzle. It confirmed a radical prediction about stellar evolution and proved the existence of matter in a state so extreme it defies earthly physics. The universe had revealed one of its most dramatic endings, not with a whisper, but with a perfectly timed beat. While pulsars revealed the quiet, precise ticking of dead stars, another discovery pointed to cosmic violence on an almost unimaginable scale. This mystery began not with a scientist's hypothesis, but with the silent watch of military satellites. During the tense years of the Cold War, the United States launched the Vela satellites, a top-secret fleet designed to detect the telltale gamma-ray signature of nuclear weapons tests in space. They succeeded in their mission, finding no evidence of forbidden explosions from other nations. Instead, they found something far stranger. The satellite's sensitive instruments began recording brief, incredibly intense flashes of gamma rays, the most powerful form of light coming from random directions in the sky. These bursts were not from Earth, and they did not repeat. They would appear without warning, blaze for a few seconds, and then vanish forever into the darkness. For decades, their origin was one of the most fiercely debated puzzles in astronomy. The central question was one of distance. Were these flashes nearby firecrackers within our own Milky Way galaxy, or were they distant cosmic supernova from the edge of the observable universe? The answer would define just how powerful these events truly were. The breakthrough finally came in the 1990s, thanks to two new eyes on the sky. NASA Compton Gamma Ray Observatory catalogued thousands of bursts, proving they were evenly distributed across the heavens, a strong hint they came from far beyond our galaxy. Then the Italian-Dutch satellite Bepo-SX performed a crucial feat. It pinpointed the location of a burst quickly enough for ground-based telescopes to swing into action. What they saw was a fading afterglow of light in a distant galaxy, billions of light years away. That single observation solved the distance debate overnight. These bursts were not local, they were the most luminous explosions in the universe since the Big Bang itself. Further work revealed there were two distinct breeds of these cosmic detonations. The long bursts, lasting more than 2 seconds, are now understood as hypernova, the catastrophic collapse of a rapidly spinning, massive star into a black hole, firing jets of energy that can be seen across the cosmos. The short bursts, lasting less than 2 seconds, are even more extreme. They are the final, violent mergers of two neutron stars, objects so dense their collision shakes the very fabric of space-time and forges heavy elements like gold and platinum. What began as a military detection of phantom explosions revealed the universe's most dramatic and creative acts of destruction. The universe's most violent explosions had a source, but its brightest lights remained a profound enigma. In the early 1960s, astronomers using radio telescopes began pinpointing strange, star-like objects that emitted powerful radio waves. They were named quasars, short for quasi-stellar radio sources. When their light was finally analyzed, it revealed something utterly baffling. Their spectral lines were shifted far into the red, a sign of the Doppler effect on a cosmic scale. This enormous redshift meant these seemingly faint points of light were not stars in our own galaxy, but objects fleeing from us at tremendous speeds, placed billions of light years away at the edge of the observable universe. The immediate problem was one of pure energy. If these objects were that distant, the calculations of their true brightness produced a number that defied belief. A single quasar, no bigger than our solar system, was outshining the combined light of every 100 billion stars in an entire galaxy. How was that even possible? What physical engine could possibly generate that much power from such a small volume of space? For over a decade, the mystery fueled wild and wonderful theories. Some scientists suggested quasars were white holes, the hypothetical opposite of a black hole, violently spewing matter into our universe. Others proposed they were the result of titanic, head-on collisions between entire galaxies, a catastrophic event releasing an unimaginable flash of energy. The truth, when it gradually solidified, was stranger than any collision and more elegant than any white hole. The only conceivable power source capable of such concentrated ferocity was a supermassive black hole, but not a black hole as a dark, passive pit. The model that finally explained everything involved a black hole of millions or even billions of solar masses, sitting at the heart of a young, chaotic galaxy. Vast clouds of gas, dust, and even entire stars from the surrounding galaxy would spiral inward, caught in the hole's immense gravity. This material does not fall straight in, it forms a seething, flattened whirlpool called an accretion disk. As particles in this disk rub against each other at near light speeds, friction heats them to temperatures of millions of degrees, causing them to glow with a blinding intensity across the entire electromagnetic spectrum, from radio waves to X-rays. Magnetic fields can also funnel some of the infalling material into powerful jets that shoot out from the poles, beaming energy across intergalactic space. A quasar, then, is not an object itself, but a brilliant symptom, the blazing signature of a supermassive black hole in its most gluttonous, active phase, a cosmic beacon shining from the universe's tumultuous youth. Quasars taught us to look for monsters at the heart of galaxies, but sometimes the deepest mysteries were hiding in our own cosmic backyard, riding on human-made machines. As the Pioneer 10 and Pioneer 11 spacecraft completed their historic grand tours of the outer planets, they began a long, silent drift into the abyss. Back on Earth, scientists tracking their radio signals noticed something deeply peculiar. Both spacecraft, now billions of miles from the Sun, were experiencing a tiny, unexplained deceleration. It was as if an invisible hand was gently tugging them back toward the inner solar system, a constant, minuscule acceleration sunward that defied all calculations of gravitational force. This was the Pioneer anomaly, a deviation so small it amounted to less than a billionth of the gravity we feel on Earth's surface, yet it was undeniably there, persisting year after year as the probes sailed toward the stars. For nearly 3 decades, this faint whisper in the data became a siren song for physicists. The discrepancy was just large enough to be real, but just small enough to be maddening. Could this be the first crack in Einstein's theory of general relativity, a sign that gravity behaved differently over vast interplanetary distances? Theorists proposed exotic ideas like modified Newtonian dynamics or the gravitational pull of unseen dark matter clustered in our solar system. The possibility that we were seeing entirely new physics from the decks of our own spacecraft was electrifying. Yet, a more cautious group of engineers and scientists suspected the answer was not in the laws of the cosmos, but in the nuts and bolts of the probes themselves. The Pioneers were powered by radioactive thermoelectric generators, essentially nuclear batteries that produced heat, which was then converted into electricity. This heat had to go somewhere, and it radiated away from the spacecraft as infrared light. The painstaking detective work began. A team led by Slava Turyshev spent years recovering old telemetry data from archaic tape formats and building a supremely detailed computer model of the Pioneer spacecraft, down to every bolt, instrument, and electrical box. They calculated not just how much heat was being emitted, but crucially where it was coming from and in which direction it was radiating. The breakthrough came when they realized the spacecraft's design was not perfectly symmetrical. The heat from the power source and the onboard electronics was not radiating evenly in all directions. More thermal photons were bouncing off the rear of the spacecraft's large parabolic antenna, pushing forward, than were emitted from the front. This anisotropic or directionally uneven thermal radiation created a tiny but constant pressure, a photon breeze that ever so slowly braked the spacecraft. It was not a mysterious pull from the sun, but a gentle push from the spacecraft's own warmth. By the 2010s, after a heroic effort of data archaeology and modeling, the anomaly was solved. The exotic theories of modified gravity faded away, replaced by a masterclass in engineering humility. The Pioneer anomaly stands as a brilliant reminder that before we invoke new laws for the universe, we must first become exquisite detectives of our own creations, listening closely to the quiet stories told by escaping heat and errant photons. The quiet warmth of the Pioneer probes was a mystery solved within our own house, but the next discovery felt like a single, sharp knock on the door from the great outside. In the late summer of 1977, at Ohio State University's Big Ear radio telescope, a routine sky survey was churning out reams of data on long, green-striped computer printouts. These were reviewed days later by a volunteer named Jerry Amon, who was scanning the alphanumeric codes representing signal strength when a sequence of characters stopped him cold. For 72 seconds, the telescope's receiver had locked onto a powerful, pure radio tone, exactly the frequency that scientists predicted an intelligent civilization might use to broadcast its presence. The signal was not random noise, it was narrowband, meaning it occupied a very specific slice of the radio spectrum, just like a human radio station. On the printout, Amon circled the remarkable string of letters and numbers, and in the margin he simply wrote one word in red pen: wow. That single, emphatic word would give the signal its immortal name. The WOW signal was everything researchers in the search for extraterrestrial intelligence, or SETI, had hoped for and nothing they could explain. It came from the direction of the constellation Sagittarius, lasted exactly as long as the Big Ear telescope's fixed gaze would allow as Earth rotation swept its view across that patch of sky, and then it vanished. It was never heard again. For decades, astronomers pointed every instrument they could toward that point in space, listening for a repeat, a pattern, anything. The silence was absolute. This single data point became a perfect cosmic riddle. Its characteristics screamed of potential artificial origin, yet its one-off nature made scientific confirmation impossible. Was it a fleeting, targeted beacon, a cosmic hello that washed over Earth and then ceased? Could it have been a reflection of a human-made satellite signal bouncing off a piece of space debris? The most tantalizing and debated explanation came much later, in 2016, when an astronomer proposed it might have been the hydrogen cloud of a passing comet that no one knew was in that region at the time. But this theory was swiftly contested, as the comets in question were not precisely where they needed to be, and their diffuse gas clouds were unlikely to produce such a strong, narrowband burst. So the mystery endures, a 47-year-old question mark circled in red ink. The WOW signal took decades even to investigate fully, and in the end, it resisted every attempt at a tidy solution. It remains the ultimate ghost in the machine, a symbol not of contact but of the profound and haunting possibility that the universe might be signaling us in ways we are only just beginning to hear and may only ever hear once. It is a reminder that some cosmic discoveries are not puzzles to be solved, but sirens that call us to keep listening. The WOW signal left us listening for a message, but some of the universe's most ancient visitors arrived not with a radio whisper, but with a brilliant, fiery announcement. For centuries, the sudden appearance of a comet with a spectacular, streaming tail was seen as an omen, a celestial herald of change. Yet by the 20th century, a more scientific mystery had taken hold. Where did these icy wanderers, especially those with orbits lasting thousands or even millions of years, truly come from? Astronomers could track the paths of short-period comets, linking them to the Kuiper belt beyond Neptune, but the trajectories of the long-period visitors told a different story. They arrived from every direction, not from the flat plane of the planets, but from a vast, three-dimensional shell of space surrounding our entire solar system. In 1950, the Dutch astronomer Jan Oort studied these paths and made a breathtaking deduction. He proposed the existence of a gigantic, spherical reservoir of icy planetesimals, a cloud so distant and tenuous it lay at the very edge of the Sun's gravitational influence. This Oort cloud, as it became known, was not a place we could ever hope to see directly. Its trillions of frozen objects, remnants from the solar system's violent birth, were simply too far away and too dark. For decades, it remained a brilliant but ghostly hypothesis, a necessary idea sketched on chalkboards to explain the comets that graced our skies. The proof would have to be indirect, a detective story written in the paths of the visitors themselves. Modern astronomical surveys and computer simulations began to trace the precise origins of long-period comets, and their journeys consistently pointed back to that distant spherical shell, gently stirred by the passing gravity of nearby stars. Then, in 2017, a pivotal piece of evidence arrived from interstellar space. The object named Oumuamua, the first known visitor from another star system, was observed tumbling past the Sun. Its trajectory and speed confirmed it was not bound to our Sun at all. While Oumuamua itself came from afar, its existence provided powerful support for the Oort cloud concept. If every star is likely surrounded by its own similar cloud of icy debris, then such interstellar travelers must be common, exactly as we are now beginning to observe. Jan Oort's theoretical cloud, envisioned from a handful of comet paths, has been vindicated as the deep freeze archive of our solar system's earliest days. It solves the riddle of our most primordial visitors, reminding us that sometimes the most profound cosmic discoveries are not made by pointing a telescope at an object, but by using the mind's eye to see the invisible architecture of space itself. Sometimes the most important discovery in history sounds like static. In the early 1960s, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were calibrating a giant horn-shaped antenna originally built for satellite communication. Their goal was to map faint radio signals from the Milky Way, but their work was plagued by a persistent, low-level hiss that came from every direction in the sky, day and night. It was a uniform microwave noise they could not eliminate. They checked every possible source of interference. They painstakingly examined the antenna itself, even scraping away layers of what they diplomatically called a white dielectric material, which was actually pigeon droppings from a pair of nesting birds. Yet the hiss remained, an inescapable whisper permeating the cosmos. Puzzled and slightly frustrated, they had stumbled upon a signal that would redefine our cosmic origin story, but they did not yet know what they were hearing. Meanwhile, just a short distance away at Princeton University, a team of physicists led by Robert Dicke had been actively searching for this exact signal. They theorized that if the universe began in a hot, dense state, a Big Bang, it should have left behind a cooled remnant of its initial fireball, a faint glow of radiation stretched by the expansion of space over billions of years into the microwave part of the spectrum. When the two groups connected, the revelation was instantaneous. That annoying, inescapable hiss was not instrument failure. It was the cosmic microwave background radiation. It was the afterglow of creation itself, cooled to just 2.7 degrees above absolute zero. This discovery transformed cosmology from a field of elegant speculation into a rigorous observational science. For the first time, we had direct, tangible evidence of a hot, dense beginning to the universe. The cosmic microwave background is a snapshot of the cosmos when it was a mere 380,000 years old, a time when it had cooled enough for atoms to form and light to travel freely for the first time. That uniform hiss is the infant universe's first photograph, its light finally reaching us after a journey of 13.8 billion years. It confirmed the Big Bang theory so decisively that it ended competing ideas like the steady-state model, which proposed a universe with no beginning. But this ancient light held even deeper secrets within its subtle imperfections, tiny fluctuations in temperature that would become the blueprints for everything we see today. That uniform hiss was the echo of the universe's birth, but within its faint warmth lay the seeds of a far deeper and darker mystery. While the cosmic microwave background confirmed how the universe began, it would soon point to a profound question about what the universe is actually made of. The first real clue to this cosmic secret didn't come from the ancient sky, but from the frantic motion of galaxies in the here and now. In the 1930s, a brilliant and cantankerous astronomer named Fritz Zwicky was studying the Coma Cluster, a vast swarm of galaxies millions of light-years across. He measured how fast these galaxies were orbiting the cluster's center, and the numbers made no sense. They were moving so incredibly fast that, according to the laws of gravity and the amount of visible starlight he could see, the entire cluster should have flown apart eons ago. There simply wasn't enough gravitational glue from the stars and gas to hold it together. Zwicky concluded there must be some other form of matter, unseen and mysterious, providing the extra gravity. He called it Dunkel Materie, dark matter. For decades, the astronomical community largely ignored his radical idea, dismissing it as an oddity or an error in measurement. It seemed too outlandish, an invisible substance holding the cosmos together. The case for dark matter would not be truly reopened until the 1970s through the meticulous, patient work of astronomer Vera Rubin. She wasn't studying clusters, but individual spiral galaxies like our own Milky Way. By carefully measuring the rotation speeds of stars at different distances from a galaxy's bright center, she expected to see a clear pattern. Just as planets in our solar system orbit slower the farther they are from the Sun, stars at the outer edges of a galaxy where visible matter thins out should orbit much more slowly than those near the crowded core. That is what Newton's laws demanded. What Rubin found, galaxy after galaxy, was a flat rotation curve. Stars on the distant, dim outskirts were whipping around just as fast as those near the brilliant center. It was as if every spiral galaxy was embedded within a gigantic, invisible sphere of mass, a hidden halo extending far beyond the last visible star. The gravity from this unseen stuff was pulling on the outer stars, speeding them up. Rubin's data was undeniable. The universe was filled with something that did not emit, absorb, or reflect light, yet it exerted a powerful gravitational grip on everything we could see. This invisible scaffolding, we now know, makes up roughly 85% of all the matter in the cosmos. So what is it? We know what it is not. It is not clouds of normal gas, not rogue planets, not black holes made from regular matter. Those would interact with light and we would see them. Dark matter appears to be something entirely new, a fundamental particle that barely notices the electromagnetic force passing through our bodies and our planet as if they were not even there. For over 50 years, this has been one of physics' greatest puzzles. The search for dark matter is a grand, multi-front endeavor. In deep underground laboratories, shielded from cosmic rays by thousands of feet of rock, ultra-sensitive detectors wait for the once-in-a-lifetime tremor that might signal a dark matter particle bumping into an atomic nucleus. In massive particle colliders like the Large Hadron Collider, scientists try to create these particles in high-energy collisions, hoping to catch a glimpse of their decay products. And in space, telescopes map the subtle distortions of distant starlight caused by dark matter's gravity bending spacetime, creating a cosmic lens. We are surrounded by an ocean of this mysterious substance, feeling its pull in the very rotation of galaxies, yet it remains as elusive as a ghost. It is the definitive proof that the universe is far stranger than it appears, a place where most of the material reality is, for now, a profound and silent enigma. Dark matter was the invisible hand sculpting galaxies, but the universe had an even more startling secret about its ultimate destiny. For most of the 20th century, cosmologists operated under one fundamental assumption, that the expansion of the universe set in motion by the Big Bang was gradually slowing down. The mutual gravitational pull of all the galaxies, stars, and even dark matter was expected to act as a cosmic brake, gently decelerating the great outward rush. The only real debate was whether there was enough matter to one day reverse the expansion entirely, leading to a big crunch, or if the universe would simply coast toward a cold, quiet halt. Then, in the late 1990s, two independent teams of astronomers set out to measure this deceleration with precision. Their tool was a specific kind of cosmic bomb known as a Type 1, a supernova. These are the thermonuclear explosions of white dwarf stars, and they have a remarkable property: they all reach roughly the same peak brightness. This makes them perfect standard candles, celestial mile markers. By measuring how bright one of these supernovae appears from Earth and knowing its true intrinsic brightness, astronomers can calculate its exact distance. By then measuring how much its light is stretched or redshifted by the expansion of space, they can determine how fast the universe was expanding at the time the star exploded. The plan was to look deep into the past at supernova billions of light years away to see how much the expansion had slowed over cosmic time. What both teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, found instead sent a shockwave through physics. The distant supernova were significantly fainter than their redshifts predicted. They were farther away than they should have been if the universe had been slowing down. There was only one possible, mind-bending conclusion: the expansion of the universe was not decelerating at all. It was speeding up. Some mysterious repulsive force was overcoming the collective gravity of everything, pushing galaxies apart at an ever-increasing rate. The universe, it seemed, had its foot on the accelerator. This force needed a name, and for lack of a better understanding, cosmologists called it dark energy. The discovery was so profound and so unexpected that the teams spent years checking and rechecking their data for errors, from intergalactic dust to possible evolution in the supernova themselves. The result held firm. In 1998, they announced their findings and the world of cosmology was turned on its head. The philosophical impact was staggering. First, it rewrote the ultimate fate of the cosmos. Instead of a big crunch or a slow freeze, the leading model now is a cold, lonely, and endless expansion, where galaxies beyond our local group will eventually be pushed so far away that their light can never reach us, leaving a future sky that is mostly black and empty. Second, and perhaps more humbling, it revealed the stunning limits of our knowledge. When we add up all the normal matter, the atoms in stars, planets, and us, it accounts for only about 5% of the universe's total energy content. Dark matter, the invisible scaffolding, makes up about 27%. The remaining 68%, the dominant component of everything, is dark energy. This enigmatic pressure infused in the fabric of space itself that is causing the cosmos to fly apart. We have a name for it, but we do not yet know what it is. Is it a cosmological constant, a property of empty space as Einstein once proposed and then discarded? Is it a dynamic field that changes over time? The discovery of the accelerating universe stands as one of the greatest surprises in modern science, a stark reminder that the cosmos is not only stranger than we imagine, but that it is actively hiding its deepest workings in plain sight. The discovery of dark energy revealed a cosmos dominated by forces we cannot see, but sometimes the most telling clues come from particles so elusive they pass through our planet as if it were a ghost. Deep underground, in a decommissioned gold mine in South Dakota, a chemist named Ray Davis was building a trap for sunlight. His target was not light itself, but the ghostly subatomic particles produced in the sun's furious core, neutrinos. According to the most trusted models of solar physics, the nuclear fusion that powers our star should flood Earth with a specific, calculable number of these particles every second. In the late 1960s, Davis's Homestake experiment began its long, quiet watch. His detector was a vast tank filled with 100,000 gallons of dry cleaning fluid. The idea was brilliant in its simplicity. On the incredibly rare occasion a neutrino from the sun interacted with a chlorine atom in the fluid, it would transform that atom into radioactive argon. By periodically flushing the tank and counting the few atoms of argon produced, Davis could count the neutrinos. After years of painstaking work, the results were in, and they were deeply unsettling. Davis was detecting only about 1/3 of the neutrinos his calculations said should be arriving from the sun. Either our understanding of the sun's inner furnace was catastrophically wrong, or something very strange was happening to the neutrinos on their 8-minute journey to Earth. This was the solar neutrino problem, and for decades it created a quiet crisis in physics. Was the sun shining differently than we thought? Teams around the world built new, ever larger detectors using different materials, from heavy water in Canada to pure gallium in Italy and Russia. Each experiment, with its own method of catching neutrinos, confirmed the shortfall. The sun was not the problem. The models of its core were proven spectacularly correct by later measurements of solar sound waves. The flaw was in our picture of the neutrino itself. The elegant, revolutionary solution came from an idea first proposed by the Italian physicist Bruno Pontecorvo. He suggested that neutrinos might not be stable, immutable particles. Instead, they could oscillate, changing their identity as they travel through space. In the standard model of particle physics, neutrinos come in 3 distinct flavors, linked to other particles: the electron neutrino, the muon neutrino, and the tau neutrino. Davis's chlorine detector could only see electron neutrinos, the kind directly made in the sun's fusion reactions. The theory of oscillation proposed that as these electron neutrinos streamed outward, they did not simply vanish. They morphed, transforming into muon and tau neutrinos, which were invisible to his experiment. This beautiful idea had one monumental implication. For neutrinos to oscillate, they must have mass, however infinitesimally small. This was a direct violation of the long-held Standard Model, which stated neutrinos were massless. The definitive proof came at the turn of the millennium from two monumental experiments. Japan's Super Kamiok detector, a giant underground chamber filled with ultra-pure water, observed neutrinos produced in Earth's atmosphere and found clear evidence they were changing type. Canada's Sudbury Neutrino Observatory, using heavy water, provided the final, clinching evidence by simultaneously measuring the total flux of all three neutrino flavors from the Sun. The numbers added up perfectly. The missing solar neutrinos had not disappeared. They were simply in disguise, wearing a different flavor by the time they reached Earth. Ray Davis's stubborn one-third count, a puzzle that lingered for over 30 years, was solved not by fixing the Sun, but by rewriting the rules for the most ghostly particle in nature. It was a triumph of patience, proving that sometimes to understand the grand machinery of a star, you must first catch the shadows it casts and learn to see them for what they truly are. The ghostly neutrino had just taught us that particles can change their very nature, but other cosmic secrets were hiding in plain sight, disguised as a simple star's disappearance. On March 10, 1977, a team of astronomers was aboard a high-flying Kuiper Airborne Observatory, a converted military cargo plane with a large telescope in its side. Their mission was precise: to watch the distant planet Uranus pass in front of a faint star, an event called an occultation. By timing exactly how the starlight vanished and reappeared, they could measure the planet's size and atmosphere with unprecedented accuracy. As they watched their instruments, the star did exactly what they expected. It blinked out as Uranus moved in front of it, but then something impossible happened. Several minutes before the main occultation, the star's light flickered, dipping briefly several times. Then, after the planet had passed and the star shone brightly again, the same series of dips occurred in reverse order. It was as if invisible moons were casting shadows, but the timing and symmetry were all wrong. In the cramped, noisy cabin of the aircraft, confusion turned into a thrilling realization. Those symmetrical dips could only mean one thing: Uranus was surrounded by a set of narrow, dark rings. Until that moment, rings were the majestic, icy signature of Saturn alone, a defining feature thought to be unique in our solar system. The discovery was utterly serendipitous, a cosmic bonus found while looking for something else entirely. It immediately rewrote the textbook. Planetary rings were not a singular marvel. They were a potential feature of other worlds, challenging every assumption about where and how such delicate structures could form and survive. Yet confirming and understanding these rings from Earth was a monumental challenge. They were incredibly dark, reflecting almost no light, and terribly narrow. For years, they remained ghostly silhouettes only seen during rare stellar occultations. The mystery of their true nature demanded a closer look. That opportunity came 9 years later, in January 1986, when NASA Voyager 2 spacecraft shot past Uranus on its grand tour of the outer planets. Its cameras revealed a ring system of stunning complexity and stark beauty. There were 11 distinct rings, most pitch black and razor-thin, some braided or elliptical, and 2 new faint rings discovered between them. Unlike Saturn's bright, icy rings, Uranus's rings were composed of dark, charcoal-colored material, likely radiation-processed organics and rock with very little reflective ice. This explained why they were nearly invisible from Earth. Voyager's data painted a picture of a dynamic, young system, possibly shepherded and shaped by the gravity of small moons orbiting within the rings themselves. The discovery of the rings of Uranus did more than just add a new feature to a distant world. It forced astronomers to broaden their theories of planetary formation and dynamics. Rings, it seemed, could arise from different violent histories, perhaps from the shattering of moons by ancient impacts or the tidal tearing apart of passing comets. What began as a few perplexing dips in starlight aboard a shaking aircraft opened a new chapter in planetary science, proving that the universe often places its most elegant answers just outside the edge of our expectations. While one star was hiding its dark rings, another was performing a slow, cosmic dance in plain sight for centuries. Long before telescopes, in the year 1596, a Dutch astronomer and pastor named David Fabricius was charting the familiar stars of the constellation Cetus, the Whale. He noticed something extraordinary, a star of the third magnitude clearly visible that simply should not have been there. No chart or record listed it. Months later, when he looked again, the star was gone. This celestial apparition would return, brightening until it could be seen with the naked eye, then fading back into the telescopic depths over a cycle of about 11 months. It was named Mera, Latin for the wonderful, and it became the first documented variable star, a beacon that refused to obey the ancient doctrine of an unchanging, perfect firmament. For over 300 years, Mera's rhythmic vanishing act was a profound cosmic riddle. What could possibly cause a star to breathe in such a slow, grand cadence? The mystery was not just in the change, but in the sheer scale of it. At its peak, Mera shines hundreds of times brighter than at its faintest. Early theories were limited by the technology of the age. Could it be a star partially eclipsed by a dark, orbiting companion? Or was it somehow shrouded by vast clouds of cosmic dust that periodically drifted into our line of sight? The true answer lay in understanding the star's very nature, and that required a new way of seeing starlight. The breakthrough came in the early 20th century with the powerful combination of spectroscopy and a deeper grasp of stellar physics. When astronomers finally dissected Mera's light, they found the signature of a cool, giant star, a sun in its deep old age. The key was in its pulsation. Mera is not being eclipsed, it is literally breathing. It is the prototype of a class of pulsating variable stars, red giants in the late, unstable stages of their lives. These aging stars have exhausted the hydrogen fuel in their cores and are now burning heavier elements in shells around a dense, inert core. This delicate balance is unstable. The star's outer layers act like a vast, slow engine, trapping radiation and causing the entire gigantic envelope to rhythmically expand and contract. As it expands, the star's surface cools and reddens, radiating its energy over a much larger area and thus appearing dimmer from our distant vantage point. Then gravity pulls the colossal atmosphere back inward, heating it as it compresses, causing the star to shine more brightly. This cycle repeats over months or years, a heartbeat signaling stellar senescence. But Mera's story does not end with its pulse. This gentle, rhythmic expansion and contraction is also a mechanism of cosmic recycling. With each pulsation, the star loses more of its outer layers, casting off great shrouds of gas and dust into the surrounding space. Over thousands of years, this process will completely strip away the star's atmosphere, leaving behind the hot, exposed core, which will then illuminate the ejected cloud, creating one of the most beautiful objects in the heavens, a planetary nebula. The solution to Mera's ancient mystery thus revealed a critical chapter in the life story of stars like our own Sun. Furthermore, because the pulsation period of these Mera-type variables is directly linked to their true intrinsic brightness, they became crucial celestial yardsticks. By measuring how bright one appears and knowing how bright it truly is from its pulse, astronomers could calculate its distance with remarkable accuracy. The wonderful, winking star that confused David Fabricius became a fundamental tool for mapping the scale of our galaxy, turning a cosmic question mark into a guiding light for exploration. Mera's rhythmic pulse was a sign of a star's old age, but a different kind of rhythm, a mathematical one, once seemed to govern the very architecture of our solar system. In the 1770s, a strange numerical pattern was noticed. If you took a simple sequence of numbers, added 4 to each, and then placed the planets at those proportional distances from the Sun, the orbits of the known worlds fell almost perfectly into line. Mercury, Venus, Earth, Mars, Jupiter, and Saturn all matched. This was the Titius-Bode law, an empirical rule with no known physical basis, a curious coincidence scribbled in the margins of astronomy texts. Yet its most tantalizing feature was a glaring gap. The pattern predicted a planet should orbit between Mars and Jupiter, a world that simply did not exist. Was the law a fluke, or was it pointing to something real, a missing piece of the cosmic puzzle? The answer came not with a flash, but with a slow, patient sweep of the sky. On the first night of the 19th century, January 1st, 1801, the Italian astronomer Giuseppe Piazzi was meticulously cataloguing stars when he found one that moved. Tracking it over successive nights, he confirmed it was a new solar system body, orbiting precisely in that predicted gap between Mars and Jupiter. He named it Ceres after the Roman goddess of agriculture. The astronomical world celebrated, the Titius-Bode law was vindicated, and a new planet had been discovered. The triumph, however, was short-lived. Just over a year later, another moving point of light was found in the same region by Heinrich Olbers. He named it Pallas. Then came Juno in 1804 and Vesta in 1807, 4 planets sharing nearly the same orbital highway. This was unprecedented and deeply confusing. For decades, astronomers wrestled with what to call these objects. They were catalogued as planets, but their small size and shared territory made them cosmic oddities. Were they fragments of a single, shattered world? Were they simply a new class of miniature planets? The mystery lingered for nearly half a century, a taxonomic headache that reflected a deeper gap in our understanding. The solution arrived not with a single revelation, but with a gradual accumulation of evidence. As telescopes improved and sky surveys became more systematic, more and more of these tiny wanderers were discovered throughout the mid-19th century. By the 1850s, there were dozens. It became clear that Ceres was not a lone planet, but the largest member of a vast swarm of rocky bodies. They were given a new name, asteroids, meaning star-like, and their home became known as the asteroid belt. The Titius-Bode law, it turned out, had not predicted a missing planet, but had instead pinpointed a cosmic construction zone where a planet failed to form. The immense gravity of nearby Jupiter, acting like a colossal gravitational bully, stirred up the primordial material in that region so violently that the small rocky bodies could never coalesce into a single world. Instead, they remain as ancient planetesimals, the leftover building blocks of the solar system. The discovery of the asteroid belt solved a 50-year puzzle and fundamentally reshaped our view of planetary formation. It showed us that our solar system is not a perfectly arranged clockwork, but a dynamic and sometimes messy construction site where the gravity of giants can dictate the fate of worlds, leaving behind a fossil record of rubble that tells the story of what might have been. The asteroid belt was a graveyard of failed planets, but other cosmic objects were hiding their true identities behind a simple, misleading name. Through his magnificent telescope in the 1780s, the great astronomer William Herschel observed a number of faint, fuzzy patches that did not behave like stars. Unlike the pinpricks of distant suns, these objects appeared as small, glowing disks, often with a round or slightly oval shape. To Herschel's eye, they bore a striking visual resemblance to the distant, greenish disk of the newly discovered planet Uranus. Believing he had found a new class of celestial object, he gave them a name that would stick for over a century: planetary nebulae. The term was a label born of visual similarity, not understanding, and it set science on a long detour. For generations, astronomers genuinely debated whether these nebulous spheres were distant solar systems in the making, perhaps vast clouds of gas and dust condensing into new planets around infant stars. The name itself became a prison for thought, locking the objects into a planetary category that felt intuitive but was fundamentally wrong. The key to their liberation would not come from a better telescope, but from a new way of dissecting light itself. The breakthrough arrived in the early 20th century with the powerful tool of spectroscopy. When astronomers finally trained their spectroscopes on these glowing disks, the story told by their light was nothing short of revolutionary. Instead of the continuous rainbow spectrum of a star or the reflected sunlight of a planet, planetary nebulae emitted light only at specific bright colors. This pattern was the unmistakable fingerprint of tenuous, excited gas. These were not solid bodies or star-forming nurseries. They were luminous shells of ionized gas, expanding into the vacuum of space at speeds of tens of kilometers per second. But what could possibly create such a beautiful, ephemeral structure? The answer tied directly to the life cycle of stars like our own Sun. A planetary nebula is the final, brilliant sigh of a dying, low to medium mass star. After spending billions of years as a stable star, it exhausts the hydrogen fuel in its core and swells into a red giant. In its unstable final throes, the star pulsates violently, ejecting its outer layers in a series of gentle stellar winds. Eventually, the hot, exposed core of the star is revealed, a white dwarf with a surface temperature exceeding 100,000 degrees. This tiny, searing ember bathes the recently ejected cloud of gas in intense ultraviolet radiation, causing it to fluoresce with glorious color like a cosmic neon sign. The iconic ring nebula, known as M57, is a perfect example. That famous donut shape is not a literal ring, but a torus or bubble of glowing gas. We are looking almost directly down the barrel of a structure that is shaped more like a cylinder or an hourglass. The central white dwarf illuminates the thicker waist of this bubble most brightly, creating the illusion of a ring to our distant eyes. This understanding solved a century of confusion in one elegant stroke. Planetary nebulae have nothing to do with planets. They are instead the glowing shrouds of dead stars, the brief, beautiful tombstones that mark the transition from a red giant to a white dwarf. This process, which takes only tens of thousands of years, a blink in cosmic time, is the destined future for our own Sun. Billions of years from now, it too will expel its outer layers, creating a planetary nebula that will briefly outshine all the other stars in our galaxy from the perspective of any distant observer, while its core cools forever as a dense, Earth-sized diamond of carbon and oxygen. The misnamed planetary nebula thus became one of astronomy's most profound corrections, revealing not the birth of worlds, but the beautiful, intricate death of familiar suns. A star's beautiful death as a planetary nebula left behind a dense, hot ember, but what happens when the ember itself is too heavy to survive? In the early 1930s, a brilliant 19-year-old Indian physicist named Subrahmanyan Chandrasekhar was sailing from Madras to Cambridge for his graduate studies. To pass the long weeks at sea, he turned his mind to a fundamental question. What is the ultimate fate of a star like our Sun once it becomes a white dwarf? Using the then-new principles of quantum mechanics and relativity, he performed a staggering calculation right there on the ship. He concluded that a white dwarf, a star supported against its own gravity by a quantum pressure called electron degeneracy, could only exist if its mass was below a specific critical value. That value was about 1.4 times the mass of our Sun. Any white dwarf with a mass greater than that limit, he reasoned, would have gravity so overwhelming it would crush this quantum pressure. The star would have no way to stop collapsing. It was a prediction of inevitable, catastrophic gravitational collapse, a one-way ticket to oblivion. When Chandrasekhar presented his findings at the Royal Astronomical Society in London, he faced not curiosity, but outright hostility from the most celebrated astrophysicist of the age, Sir Arthur Eddington. Eddington, who had famously confirmed Einstein's theory of general relativity, found the idea of unlimited collapse philosophically and physically repugnant. He publicly ridiculed Chandrasekhar's work, calling it stellar buffoonery and arguing there must be some as yet unknown law of nature that would prevent such a monstrous outcome. For Eddington, the universe simply would not permit a star to vanish into a point of infinite density. The confrontation was brutal and personal, casting a long shadow over Chandrasekhar's early career and stalling the acceptance of his idea for decades. The scientific community, swayed by Eddington's towering authority, largely sided with the established giant against the young theorist, yet the mathematics was relentless. Over the following 30 years, as nuclear physics matured and our understanding of stellar evolution deepened, the evidence for Chandrasekhar's limit became undeniable. Observations of white dwarfs consistently showed they all fell below that critical mass. The limit explained why white dwarfs were the final state for only lower mass stars. More importantly, it forced astronomers to ask the terrifying question Eddington refused to entertain. If a dying star's core exceeded 1.4 solar masses, what then? The answer led directly to the prediction of even more exotic stellar corpses. Theorists like Robert Oppenheimer and George Volkoff realized that for slightly more massive cores, collapse would continue until a new, even fiercer quantum pressure from neutrons could halt it, creating a neutron star. And for the most massive cores, even neutron pressure would fail, leading to the formation of a black hole, an object where gravity wins completely. Chandrasekhar's lonely calculation on a ship had mapped the boundary between a stable stellar gravestone and the abyss. His vindication came slowly but decisively, culminating in the Nobel Prize in Physics in 1983, a recognition delayed by half a century. The limit that bears his name stands as a monument to the power of pure reason, a simple number that dictates whether a star ends its life as a diamond in the sky or vanishes into a hole in space-time. Chandrasekhar's limit defined the boundary between life and death for stars, but it left a deeper question unanswered. Where did the very atoms that make up our world come from? The hydrogen and helium were forged in the Big Bang, and lighter elements like carbon and oxygen are cooked in the hearts of ordinary stars. But the origin of the heaviest elements, gold, platinum, uranium, the dense metals that form our jewelry, our electronics, and even parts of our bones, was a cosmic mystery for generations. They cannot be made in the steady, stable furnaces of living stars. Creating these heavy nuclei requires a flood of free neutrons, subatomic particles that can slam into existing atoms before they have a chance to decay, building up weightier and weightier elements in a frantic, violent assembly line. But where in the universe does such a neutron deluge occur? The theoretical answer arrived in a landmark paper published in 1957, authored by four towering figures in astrophysics: Margaret and Geoffrey Burbidge, William Fowler, and Fred Hoyle. Their work, often called B2FH, mapped out the entire cosmic origin of the elements. They identified a specific mechanism called the rapid neutron capture process, or the R process. This required an environment of extreme density and temperature, where neutrons were so abundant and conditions so chaotic that atomic nuclei could gorge themselves, capturing neutrons in a fraction of a second before radioactively decaying into stable, heavy elements. The paper was a masterpiece of theoretical prediction, but for 60 years it pointed to a blank spot on the cosmic map. Where was this incredible neutron factory? Astronomers proposed candidates: the violent cores of collapsing supernova, or perhaps the cataclysmic mergers of the densest objects in the universe, neutron stars. The debate simmered for decades, a fundamental question about our own composition hanging in the balance. Then, on August 17, 2017, the universe provided the invoice. Gravitational wave observatories on Earth detected a distinctive ripple in spacetime, a signal named GW170817. It was the chirp of two neutron stars, each more massive than our Sun, but only the size of a city, spiraling together in a final, deadly dance over 130 million light-years away. For the first time in history, astronomers were alerted immediately, and telescopes across the globe and in space swiveled to that patch of sky. What they saw was a kilonova, a flash of light 1,000 times brighter than a typical nova. The spectrum of that light told the definitive story. It was rich with the spectroscopic signatures of heavy elements like gold, platinum, and lanthanides, created in the radioactive debris ejected from the collision. The data was a perfect match for the predictions of the R process. In that single multi-messenger observation, a 60-year-old mystery was solved. The gravitational waves confirmed the nature of the event, a neutron-star merger, and the light revealed its chemical product. These cosmic collisions are the primary forges for the heaviest elements in the universe. The gold in a wedding ring, the platinum in a catalytic converter, were likely born in the fiery aftermath of two dead stars smashing together billions of years ago, their enriched debris eventually seeding the cloud that would form our solar system. We are quite literally stardust, but the most precious parts of us are the ashes of the most violent reunions imaginable. Our own galaxy is not a stationary island in the void, but a ship adrift in a vast cosmic current. Beginning in the 1970s, astronomers creating three-dimensional maps of the universe noticed something deeply unsettling. Our entire local group of galaxies, along with thousands of others, was not moving randomly. Everything was streaming in the same direction, toward a specific, mysterious point in the sky near the constellations Centaurus and Hydra, at a staggering speed of over 600 kilometers per second. This was not the general expansion of the universe which carries galaxies apart. This was a specific, targeted river of motion, as if some unimaginable mass was reeling us in. The invisible source of this pull was given a name that captured both its power and its mystery, the Great Attractor. What colossal structure, hidden from our view, could command the motion of millions of galaxies? The immediate problem was a cosmic blind spot. The direction of this pull pointed directly into the zone of avoidance, an area of the sky obscured by the thick dust and brilliant stars of our own Milky Way's galactic plane. It was like trying to see a distant mountain range through a dense, permanent fog. For years, the Great Attractor was a gravitational phantom, its influence measurable but its form completely invisible. The solution required new eyes that could see through the galactic murk. In the 1990s and 2000s, instruments like the infrared astronomical satellite and later X-ray observatories finally pierced the veil. Infrared light passes through dust, and X-rays are emitted by the superheated gas that fills the spaces between galaxies in massive clusters. What they revealed was not a single monolithic superobject, but something even more grand. The Great Attractor is a gravitational focal point, the dense core of our local supercluster, which we now call Laniakea, a Hawaiian word meaning immense heaven. At its heart lies the Norma cluster, a massive congregation of galaxies, along with other rich clusters like the Centaurus cluster. This entire region, hundreds of millions of light years across, contains a total mass equivalent to tens of thousands of Milky Ways. The pull we feel is the collective gravity of this immense concentration of both normal matter and dark matter, the central weight of our cosmic neighborhood. The mystery of our galaxy's peculiar motion was solved not by finding a single attractor, but by mapping the continental structure of the cosmos itself. We are not being pulled toward a secret monster, but are flowing, along with countless other galaxies, toward the deepest valley in the local gravitational landscape, a testament to the fact that even on the grandest scales, gravity is the great sculptor, carving streams of galaxies across the emptiness of space. The gravitational pull of Laniakea shapes our local journey, but for generations a far grander question haunted cosmology, the ultimate destination of the entire universe. Throughout the 20th century, scientists wrestled with two starkly different visions of cosmic destiny, each a direct consequence of the Big Bang's initial push. The first was the Big Crunch, a dramatic and fiery end. If the density of matter in the cosmos was high enough, the collective gravity of all galaxies, stars, and dark matter would eventually overcome the expansion. The universe would slow, halt, and then begin collapsing in on itself, galaxies would rush together, temperatures would soar, and all of space would ultimately contract back into a singularity of infinite density, a mirror image of its birth. It was a cyclical vision, suggesting the possibility of an eternal series of cosmic rebounds. The opposing vision was the heat death, a quiet and chilling finale. If the universe's density was too low, gravity would never be strong enough to reverse the expansion. The cosmos would simply keep expanding forever, thinning out into an ever colder, darker void. Stars would burn through their fuel, galaxies would fade, black holes would evaporate, and over trillions upon trillions of years, all energy gradients would smooth out into a uniform, lukewarm sea of particles drifting infinitely apart. This was not an explosion, but an eternal, silent dissipation. For decades, this was the great cosmological fork in the road, a debate about the fundamental geometry and content of everything. The answer hinged on a critical number, the omega parameter, the ratio of the universe's actual density to the critical density needed to just barely halt the expansion. Measuring this number was the work of a century, a painstaking census of all the light and matter we could see. The shocking discovery of dark energy and the accelerating expansion did not just add a new ingredient to the cosmic recipe, it shattered the terms of the old debate entirely. The universe was not merely expanding, it was accelerating, meaning some form of repulsive energy was woven into the fabric of space itself, actively pushing galaxies apart. This discovery decisively tipped the scales. The fate of the cosmos is no longer a question of gravity versus a coasting expansion. The repulsive force of dark energy appears to be a permanent feature, a constant or even growing influence that will dominate forever. The verdict from supernova, the cosmic microwave background, and large-scale galaxy surveys is now overwhelming. The universe will expand without end, growing colder and lonelier with each passing eon. The big crunch is off the table. Our destiny is the heat death, a gradual fade to black on a timescale so vast it defies human comprehension. The resolution of this decades-long debate is profoundly humbling. It tells us that the story of the cosmos is not a dramatic cycle of fire and rebirth, but a one-way journey from a hot, dense beginning to an eternal, silent and cold stillness. All structure, all life, all memory will one day be erased by the relentless, accelerating expansion of an empty stage. The accelerating universe writes our distant future, but one of the most captivating cosmic mysteries was born from a simple, hopeful misinterpretation of our nearest neighbor. In 1877, the Italian astronomer Giovanni Schiaparelli trained his telescope on Mars during a particularly favorable close approach. As he sketched the planet's ochre surface, he noted a network of fine, dark lines crisscrossing the bright deserts. He called them canali, an Italian word that simply means channels, a neutral term for natural features. But when his work was translated into English, canali became canals, a word loaded with implication. Canals are not natural, they are engineered, the products of intelligence and purpose. This single linguistic shift ignited a firestorm of speculation that would burn for nearly a century. The idea was seized and passionately championed by the American astronomer Percival Lowell. From his observatory in Flagstaff, Arizona, Lowell produced elaborate, detailed maps of Mars covered in hundreds of these straight, geometric lines connecting dark patches he interpreted as oases. He wove a compelling, tragic narrative of a dying world, where a desperate, advanced civilization had constructed a planet-wide irrigation system to channel water from the polar ice caps to their parched cities. Lowell's vision was not fringe science, it was a mainstream cultural phenomenon. His books and lectures captured the public imagination, seeding stories of Martian engineers into novels, newspapers, and the collective consciousness. For decades, the idea of an inhabited Mars, a world with a history as rich and dramatic as our own, felt tantalizingly possible. The mystery persisted because it was rooted in a genuine perceptual puzzle. Under the unstable, shimmering air of Earth's atmosphere, even through powerful telescopes, Mars was a tiny, shimmering ochre disk. The human visual system is a pattern-making machine, hardwired to connect dots and infer lines. When observers strained to see, their brains unconsciously linked faint, indistinct smudges, mountain ranges, crater chains, and dust streaks into the straight, artificial-seeming lines they half expected to find. It was a perfect storm of optical illusion, physiological limitation, and profound wishful thinking. The resolution came not from better earthly telescopes, but from leaving our atmosphere behind. In 1965, NASA Mariner 4 spacecraft flew past Mars and took the first close-up images. They revealed a barren, cratered world, lunar and desolate. There were no canals, no vast geometric networks. The images showed a natural, complex landscape of mountains, valleys, and ancient impact scars, but nothing resembling the engineered waterways of Lowell's maps. The final, definitive proof came a decade later with the Viking orbiters, which mapped the entire planet in stunning detail. Their photographs showed the truth in crisp, unambiguous clarity. The canals were simply not there. They had never existed. The great Martian civilization was a phantom, a story we told ourselves by connecting cosmic dots that were never actually connected. This decades-long mystery stands as a profound lesson in scientific humility. It reminds us that our tools of perception, both mechanical and biological, are fallible, and that our deepest hopes can shape what we believe we see. The canals of Mars were a mirror, reflecting not the geology of another world, but the boundless human desire to find company in the cosmic dark. The phantom canals of Mars were a story we told ourselves, but the true cosmic monsters were lurking in the mathematics all along. The idea of a black hole was born not from a telescope but from a thought experiment. In 1783, an English clergyman and natural philosopher named John Michell pondered Isaac Newton's laws of light and gravity. He reasoned that if a star were massive enough, its gravitational pull would be so strong that not even light could escape. He called these hypothetical objects dark stars, invisible prisons for light itself. It was a brilliant, eerie speculation, but without the right mathematical framework, it remained a curious footnote for over a century. The concept was truly reborn from the ashes of a world war. In 1916, just months after Albert Einstein published his theory of general relativity, a German physicist and soldier named Karl Schwarzschild found an exact solution to Einstein's fiendishly complex equations. From the trenches of the Eastern Front, he calculated that if a mass were compressed into a sufficiently tiny sphere, space-time would curve so severely that it would pinch off entirely, creating a boundary of no return. This boundary, the event horizon, was the point where escape velocity exceeded the speed of light. The mathematics was pristine and inescapable, but to most scientists, including Einstein himself, it was a disturbing abstraction. They believed such an extreme state of matter was physically impossible, a mathematical ghost that nature would never permit. For nearly 5 decades, black holes were relegated to the fringes of theoretical physics, a bizarre extreme with no place in the real cosmos. The turning point arrived with a piercing scream from the constellation Cygnus. In 1964, a sounding rocket detected a powerful, fluctuating source of X-rays named Cygnus X1. This was unusual because X-rays are typically produced by incredibly hot, violent processes. Astronomers soon pinpointed its location to a brilliant blue supergiant star. As they studied this star's orbit, they found it was waltzing with an unseen companion, an invisible object with a mass at least 9 times greater than our Sun, all crammed into a volume smaller than a city. The only thing that could possibly be so massive, so dark, and so compact was a black hole. The X-rays were the final death cry of matter from the supergiant star, torn away by the hole's immense gravity, heated to millions of degrees as it spiraled into the accretion disk before vanishing forever across the event horizon. It was not a mathematical fiction, it was a cosmic vampire caught in the act. That single observation changed everything. Over the following decades, evidence became overwhelming. Stellar mass black holes, the corpses of massive stars, were found peppered throughout our galaxy. Even more profound was the realization that a supermassive black hole, with the weight of millions of suns, lurked at the heart of nearly every large galaxy, including our own Milky Way. These behemoths explain the furious energy of quasars and govern the orbits of stars at the galactic center. The final, breathtaking confirmation came in April 2019. The Event Horizon Telescope, a planet-sized array of radio observatories, presented the world with an image that was once thought impossible: a fiery ring of light surrounding the dark shadow of the supermassive black hole at the center of the galaxy M87. That iconic image was the silhouette of the event horizon itself, the point of no return made visible. In just over 2 centuries, the black hole journeyed from a clergyman's speculation to a soldier's equation, from a theoretical ghost to an observed predator, and finally to a portrait of the ultimate cosmic mystery. The search for cosmic monsters led us to black holes, but a much quieter hunt was unfolding at the frozen edge of our own solar system. For nearly a century after Neptune's discovery, astronomers were convinced something was tugging at the orbits of the outer planets. They called this hypothetical world Planet X, a giant hidden in the dark. The search culminated in 1930 when a young astronomer at the Lowell Observatory, Clyde Tombaugh, found a faint, slow-moving dot of light. It was named Pluto, and for generations it held the honored title of the 9th planet. Yet from the very beginning, Pluto was an oddity. It was far too small, and its orbit far too tilted and elliptical to be the gravitational giant they were looking for. The mystery of Planet X was not solved by Pluto's discovery, it was merely postponed. The real answer would require us to look not for one large world, but for a multitude of small ones. That shift in perspective began in the early 1990s with new, powerful telescopes and sensitive electronic detectors. Astronomers started finding other small, icy bodies orbiting in the deep freeze beyond Neptune. The first, discovered in 1992, was given the provisional designation 1992 QB1. Soon more were found, dozens, then hundreds. These were not random wanderers, they shared a broad, donut-shaped region of space, a belt of primordial leftovers from the solar system's formation. This was the Kuiper Belt, a theoretical concept proposed by the Dutch-American astronomer Gerard Kuiper decades earlier, now made gloriously real. Pluto, it turned out, was not a solitary planet. It was simply the largest known member of this vast swarm. This realization sparked a quiet, decades-long identity crisis in astronomy. If Pluto was a planet, then what were these other, nearly identical objects? The crisis became unavoidable in 2005 with the discovery of an object initially thought to be even larger than Pluto, later named Eris. The astronomical community faced a stark choice: either declare Eris the 10th planet or reconsider what the word planet truly meant. The debate came to a head at the International Astronomical Union's meeting in 2006. After passionate discussion, they established a new 3-part definition. A planet must orbit the Sun, be massive enough for its own gravity to pull it into a round shape, and crucially, it must have cleared its orbital neighborhood of other debris. Pluto, sharing its orbital highway with thousands of other Kuiper Belt objects, failed this final test. It was reclassified as a dwarf planet, a new and important category. This was not a demotion, but a promotion in understanding. Pluto became a king, the brightest and first discovered of a vast kingdom of icy worlds at the edge of our solar system. The decades-long puzzle of Planet X was solved not by finding one missing giant, but by discovering an entire new architectural zone of our cosmic home, a frozen archive holding clues to the solar system's earliest days. The galactic core should have been the brightest jewel in our sky, a dense hub of ancient stars. Instead, when astronomers first turned their radio telescopes toward the constellation Sagittarius, they found a thick, obscuring veil of dust and gas. Yet behind that veil, something powerful was broadcasting. They pinpointed a strange, compact, and incredibly bright source of radio waves, naming it Sagittarius, a star. For decades, its true nature was hidden, a persistent radio whisper from the heart of our own cosmic city. What could possibly produce such intense, focused emission in that chaotic region? Was it a tight knot of young, massive stars, or perhaps the remnant of a recent, colossal supernova? The central mystery was one of scale and power, confined to a region of space smaller than our solar system, yet radiating with the energy of millions of suns. The answer would require new eyes that could see through the galactic smog. Visible light was useless, blocked by the intervening dust. The breakthrough came with observations in the infrared part of the spectrum. Infrared light, with its longer wavelengths, can slip between dust grains like a whisper through a wall. Beginning in the 1990s, teams using ever larger telescopes in Chile and Hawaii began a monumental project. They started mapping the individual stars in the crowded core, not for a single snapshot, but year after year after year. This was a celestial stakeout, a patient vigil to trace the motions of stars in the most crowded neighborhood of the galaxy. What they saw over more than 2 decades of observation was nothing short of breathtaking. A handful of stars, now known as the S-stars, were caught in a frenzied gravitational waltz. They were not moving in calm, orderly orbits. They were whipping around an invisible focal point at speeds exceeding 5,000 kilometers per second, tracing elliptical loops that brought them perilously close to something unseen. One star, known as S2, completed a full orbit in just 16 years, a blink in cosmic time. By meticulously plotting these insane trajectories, astronomers could apply the simple, unyielding laws of Kepler and Newton. They could calculate the mass of the object that held these stars in its thrall. The numbers were staggering. The invisible anchor had a mass of over 4 million times that of our Sun, all crammed into a volume of space smaller than the orbit of Mercury. No cluster of stars, no nebula, no known object could be that massive and that small. The only possible explanation was a supermassive black hole. The radio source Sagittarius, a star, was not just a beacon. It was the signature of the black hole's immediate environment, the faint radio glow from the hot, magnetized gas eternally spiraling toward the event horizon. The decades-long mystery of the galactic center's radio whisper was solved. We now know with certainty that a gravitational monster, quiet and dark, sits at the heart of the Milky Way, a sleeping giant whose gentle pull orchestrates the grand dance of our entire galaxy. This discovery did more than solve a local puzzle. It confirmed a profound universal truth. Supermassive black holes are not cosmic accidents. They are the fundamental engines, the silent anchors, at the center of nearly every large galaxy, including our own. The silent giant at our galaxy's heart governs the grand motions of billions of stars, but a far subtler anomaly, a tiny wobble in the path of a single world, would ultimately shake the foundations of physics itself. For centuries, Mercury was a puzzle to celestial cartographers. As the innermost planet, its orbit is a pronounced ellipse, bringing it close to the sun's glare and making precise observation a challenge. Yet by the mid-19th century, astronomers armed with increasingly accurate telescopes had mapped its path with exquisite care. They confirmed a phenomenon known as orbital precession. Like a spirograph drawing slowly turning, the elliptical path of Mercury itself was rotating, its point of closest approach to the Sun shifting forward over time. This was expected. The gravitational tug of the other planets, particularly Venus and Jupiter, pulls on Mercury, causing its orbit to precess. Newton's laws of gravity allowed for a precise calculation of this effect. But the numbers never matched. The observed precession was minutely faster than the predicted one. the discrepancy was a whisper in the data, a mere 43 arcseconds of angular shift per century. In the vastness of the solar system, this is an almost imperceptible drift, less than the width of a human hair held at arm's length. But it was persistent, a tiny flaw in the otherwise perfect clockwork of Newtonian prediction that would not go away. For decades, this anomaly was a quiet thorn in the side of astronomy. The most popular solution seemed elegantly simple. If an unseen source of gravity was tugging on Mercury, it could explain the extra precession. Astronomers postulated the existence of a small planet, or perhaps a band of asteroids, orbiting inside Mercury's path. They even gave this hypothetical world a name, Vulcan, and for years, diligent observers scanned the sky near the Sun during solar eclipses, hoping to catch a glimpse of the hidden culprit. But Vulcan was never found. The mystery of those missing 43 arcseconds lingered, a testament to the unsettling possibility that our understanding of gravity itself might be incomplete. The solution arrived not from a new telescope, but from a radical new vision of the cosmos. In 1915, Albert Einstein completed his general theory of relativity. In this framework, gravity is not a mysterious force acting across distance, but the curvature of spacetime itself caused by mass and energy. A planet like Mercury follows the straightest possible path, a geodesic, through this curved geometry. Einstein performed the calculations for Mercury's orbit within this new model. The result was breathtaking. The mathematics of curved spacetime naturally produced an extra contribution to the planet's orbital precession, an exact addition of 43 arcseconds per century. The number matched the observation perfectly. No hidden planet was needed. The anomaly was not an error in observation or a missing mass, but a signature of the Sun's mass warping the very stage upon which Mercury moved. This was the first critical test passed by general relativity. A tiny, nagging discrepancy that had puzzled astronomers for generations became the first concrete proof that our universe operates by rules far more profound and strange than Newton could have envisioned. Mercury's wobble was no longer a problem. It was a message written in the motion of a tiny world, that space and time are not a rigid backdrop, but a dynamic fabric shaped by the stars themselves. Mercury's wobble proved space itself could bend, but a far more direct assault was raining down on Earth from the void, an invisible hail of atomic shrapnel. In 1912, an Austrian physicist named Victor Hess made a daring series of balloon flights, ascending high into the atmosphere with an electroscope, a device that measures radiation. His goal was to understand why the air itself seemed slightly ionized, even far from any known radioactive source on the ground. To his astonishment, the radiation levels did not decrease as he rose, they increased dramatically. The source was not below, but above. Hess had discovered that Earth is under constant bombardment from deep space, a torrent of high-speed atomic nuclei he named cosmic rays. This discovery opened a new window on the universe, but it also posed an immediate and profound mystery. Where were these invisible bullets coming from? For decades, the search for their origin was a cosmic detective story with a maddening twist. Cosmic rays are not rays of light. They are charged particles, mostly protons and atomic nuclei, hurtling through space at nearly the speed of light. And because they carry an electric charge, they become puppets of magnetic fields. The Milky Way is threaded with a weak, tangled web of magnetic fields, and every time one of these particles encounters a magnetic strand, its path is bent. By the time a cosmic ray finally strikes Earth's atmosphere, it has been scrambled and redirected so many times that it is utterly impossible to trace its trajectory back to its birthplace. The source was perfectly masked. The early suspects were obvious. Our own sun was a prime candidate, and indeed, solar flares do emit bursts of lower energy cosmic rays. But the sun could not account for the most powerful particles, those with energies millions of times greater than anything we can produce in our largest particle colliders. These ultra-high-energy cosmic rays were clearly coming from beyond our solar system, but from where, the investigation required a shift in strategy. Since we could not follow the particles back, we had to look for the cosmic factories that could possibly create them. Theorists knew that to accelerate a particle to such phenomenal energies required unimaginably powerful natural accelerators, places of extreme violence and magnetic chaos. Within our own galaxy, the expanding shockwaves from supernova explosions emerged as a leading suspect. For a century, a supernova's blast wave plows through interstellar space at thousands of kilometers per second, and within that turbulent, magnetized front, particles can be trapped, bouncing back and forth like rubber balls in a collapsing hallway, gaining a tremendous speed boost with each crossing. This process, called diffusive shock acceleration, could explain the bulk of the galactic cosmic rays we detect. But the very highest energy particles, the rare giants that carry the energy of a well-thrown baseball in a single atomic nucleus, presented a problem. The Milky Way is not large enough to contain them. A particle with that much energy would be flung out of our galaxy by its own magnetic fields before it could reach us. These cosmic cannonballs had to be coming from outside, from extragalactic monsters. The modern resolution to this century-old mystery is a layered one, a story of multiple origins. Lower energy cosmic rays come from our Sun. The moderate galactic ones are now widely believed to be born in the expanding remnants of supernova, the graves of massive stars. But the ultra-high-energy particles, the true outliers, are thought to originate in the most violent places in the universe, far beyond our galaxy. The prime suspects are active galactic nuclei, where supermassive black holes launch jets of plasma at nearly light speed, and perhaps from cataclysmic events like neutron star mergers or gamma-ray bursts. The final proof is arriving now through the new era of multi-messenger astronomy. We are no longer relying on the scrambled cosmic rays alone. When these particles are accelerated, they also produce gamma rays and neutrinos. Unlike charged particles, gamma rays and neutrinos travel in straight lines, pointing directly back to their source. By detecting a burst of high-energy neutrinos from a specific direction, and then matching it with a flare of gamma rays from a distant blazar, a type of active galaxy, scientists are finally, definitively, beginning to pin down the cosmic accelerators. The invisible hail that Victor Hess discovered over a century ago is slowly revealing the addresses of its furious factories, proving that the universe is not just a realm of light, but a storm of atomic fragments fired from its most violent hearts. Even as we map the invisible accelerators of the cosmos, a fundamental number is refusing to agree with itself. This is the Hubble tension, a modern crisis that asks how fast the universe is expanding right now. The number is called the Hubble constant, and it is the single most important speedometer for the cosmos, setting the scale for everything from the age of the universe to the vast distances between galaxies. For over a century, astronomers have worked to pin down its exact value, and today we have two of the most precise measurement techniques in the history of science. Yet they are telling us two different stories. The first method looks back to the infant universe, to the cosmic microwave background radiation. By studying the tiny temperature fluctuations in that ancient afterglow with satellites like Planck, cosmologists can run the cosmic film backward, using our well-tested model of the Big Bang to predict how fast the universe should be expanding today. This gives a very specific, elegant number. The second method looks at the universe around us now. Astronomers use brilliant stellar explosions, type 1, a supernova, as standard candles to measure the distances to nearby galaxies. By comparing those distances to how much the light from those galaxies is stretched by the expansion, they directly measure the current expansion rate. This too gives a precise, confident number. The problem is these two numbers do not match. The local supernova-based measurement says the universe is expanding significantly faster than the pristine early universe data predicts. The discrepancy is not large, only a few percent, but it is stubborn. It has persisted through years of ever more precise observations, surviving intense scrutiny and checks for hidden errors. This is not a case of sloppy measurements. It is a whisper of a crack in our most successful model of the cosmos, the lambda cold dark matter model. The implications are profound. This tension suggests that something in our cosmic recipe is incomplete or slightly wrong. Perhaps dark energy is not a constant, but a dynamic force that has changed strength over the life of the universe. Maybe neutrinos, those ghostly particles, are more exotic than we think, or there is an additional, unknown type of radiation that flooded the early cosmos and altered its expansion history. Some have even speculated about subtle properties of dark matter itself. Each possibility represents a doorway to new physics, a frontier beyond our current understanding. For decades, this was a quiet discrepancy buried in uncertainty, but today it has sharpened into one of cosmology's most urgent and exciting puzzles. It is a mystery that took the better part of a century to refine into its current, acute form, and it remains actively, vibrantly unsolved, driving a global race with new telescopes and space missions designed specifically to listen to what this cosmic disagreement is trying to tell us. Buried in the data from a long-forgotten sky survey, a single spike of energy waited 6 years for someone to notice. It was 2007 when an astronomer named Duncan Lorimer, reviewing archived observations from the Parkes radio telescope in Australia, found it. The signal was a blast of radio waves that lasted just 5 milliseconds, a cosmic blink. But in that fleeting instant, it released more energy than our sun emits in 80 days. It came from somewhere deep in intergalactic space, and then it was gone. This was the first documented fast radio burst, a Lorimer burst, a solitary data point so bizarre many wondered if it was a glitch, an instrument's ghost. For years it stood alone, a perfect, unsolved anomaly. Then the floodgates opened, as radio telescopes around the world began actively searching for these transient events. More were found. Dozens, then hundreds. Each was a brilliant, milliseconds-long flash from a random point in the sky, a flash that could outshine 1 billion suns in radio light. The mystery deepened with every new detection. Some bursts were one-off events, cosmic firecrackers that detonated and vanished. Others, astonishingly, repeated. They would flash from the same patch of sky, sometimes in a frantic, unpredictable pattern, sometimes with a steady, clockwork cadence. This repetition was a crucial clue. It ruled out any explanation involving a single, catastrophic destruction, like the collision of 2 neutron stars. Whatever was making these bursts was surviving the event, capable of firing again and again. So what cosmic engine could possibly produce such staggering, focused energy in a repeating cycle? The theories were as wild as the phenomenon itself. Could they be the death cries of evaporating black holes? The colossal energy discharges from collapsing cosmic strings, theoretical defects in spacetime, or, given their brief, powerful, and structured nature, were they perhaps the signature of an advanced civilization, beaming propulsion power across the galaxy? For over a decade, the true nature of fast radio bursts was a playground for the most exotic ideas in astrophysics. The turning point came from an event much closer to home. In April 2020, a highly magnetized neutron star, a magnetar, within our own Milky Way galaxy underwent a violent episode. It unleashed a powerful X-ray burst, and at the same moment, radio telescopes detected a fast radio burst emanating from the same object. This was the smoking gun. For the first time, an FRB was definitively linked to a known celestial object. Magnetars are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's, the most powerful magnets in the universe. The theory is that these fields are so intense they can twist the star's crust, causing starquakes that release titanic flares. In the chaotic plasma surrounding the magnetar, these eruptions could generate the incredibly bright, short-lived radio flashes we see as FRBs. This discovery provided a compelling, natural explanation for at least some of these mysterious signals. Yet the puzzle is far from complete. The extragalactic FRBs are vastly more energetic than the one from our galactic magnetar. Do they come from younger, more violent magnetars in distant galaxies, or are there multiple cosmic factories at work? The repeating bursts, some with complex patterns, suggest environments of extreme and dynamic magnetic chaos, perhaps around a newborn black hole or within the turbulent wreckage of a stellar merger. Decades after that first lonely spike was found in an archive, fast radio bursts have transformed from a curious glitch into an entirely new branch of astronomy. They are not one mystery, but many. Each millisecond flash a coded message about the most violent and magnetically ferocious corners of the cosmos, a message we are only just beginning to decipher. The universe's most violent flashes of radio energy were a puzzle of extreme physics, but a quieter, more personal mystery was written in the very rocks beneath our feet. In 1972, astronomers Carl Sagan and George Mullen highlighted a profound contradiction in our own planet's history. According to the well-established models of stellar evolution, our Sun has been steadily growing brighter over its 4.6 billion-year lifetime. When Earth was young, roughly 3 to 4 billion years ago, our star was about 30% fainter than it is today. If you take our current climate system and simply dial back the sunlight by that amount, you get a straightforward and chilling result, a completely frozen world. An icy ball locked in a permanent global winter with average temperatures far below the freezing point of water. Yet the geological record tells a completely different and warmer story. Ancient sedimentary rocks, some dating back 3.8 billion years, show clear ripple marks and other features that could only have formed in liquid water. Even more compelling, fossil evidence places the earliest known life forms, like stromatolites built by cyanobacteria, in shallow, sunlit seas around 3.5 billion years ago. For decades, this was the faint young sun paradox, a glaring mismatch between the cold, hard physics of stars and the warm, wet evidence written in stone. How could a fainter sun have kept Earth from becoming a permanent snowball? The solution could not lie with the sun itself. The models of its steady brightening were and remain rock solid. The answer had to be in Earth's own blanket, its early atmosphere. For a long time, scientists assumed our planet's original air was similar to today's, dominated by nitrogen and oxygen. But that mix creates a relatively weak greenhouse effect, insufficient to compensate for a 30% dimmer sun. The breakthrough in thinking was to realize that Earth's infancy was a chemically alien place. The leading theory proposes that our primordial atmosphere was much richer in potent greenhouse gases, particularly carbon dioxide and methane. These gases, spewed from a hyperactive world of rampant volcanism and later produced by the earliest microbial life, would have acted like a vastly thicker thermal blanket. They would have trapped far more of the sun's diminished heat, creating a powerful greenhouse effect strong enough to keep the global thermostat above freezing. This solution elegantly bridges astronomy, geology, and climatology. It tells us that our planet's habitability was not a given but a precarious balancing act. A colder star demanded a warmer coat, and Earth provided it through its own dynamic geology and perhaps through the metabolic activity of its first living inhabitants. The paradox took decades to resolve because it required us to think of Earth not as a static stage for life, but as a participant in a complex, co-evolutionary dance with its star, where the air itself was the key to unlocking a faint sun's warmth. The ghostly neutrino had finally been given a name and a face, but proving its true nature demanded a cathedral built a mile underground. Solving the solar neutrino problem was not a matter of one brilliant experiment, but a global marathon of engineering audacity. The first hints of oscillation came from Japan inside a chamber of breathtaking scale. Super Kamiok, and was a cavern filled with 50,000 tons of ultra-pure water, lined with 13,000 light-sensitive eyes. Its purpose was to catch the faint blue flash of Cherenkov radiation, a sort of optical sonic boom created when a neutrino interacts with the water and produces a charged particle moving faster than light can travel in that medium. By 1998, Super K had seen something profound. It was detecting neutrinos created not in the Sun, but in Earth's own atmosphere as cosmic rays struck the air. And the numbers were off. It found fewer muon neutrinos coming up through the planet than coming down from above. The only plausible explanation was that the ones traveling the longer path through the Earth had more time to oscillate to change into tau neutrinos, which the detector could not see. This was powerful, indirect evidence, but for the solar neutrinos, the final, unshakable proof required a different kind of alchemy. That proof came from a mine in Ontario, 2 kilometers beneath the Canadian Shield. The Sudbury Neutrino Observatory, or SNO, was an engineering marvel built around 1,000 tons of heavy water, a substance where the hydrogen atoms have an extra neutron. This rare and precious material, on loan from Canada's nuclear energy program, was the key. Heavy water gave SNO a unique talent. It could perform 3 separate measurements simultaneously. It could detect only electron neutrinos, the kind the Sun makes, through one type of interaction. It could detect all 3 flavors of neutrinos through a different, neutral current interaction. And it could also detect them via charged currents that were sensitive to a combination of flavors. This triple threat capability meant SNO could, for the first time in history, take a complete census of the solar neutrino population arriving from the Sun. The results, announced in 2001 and refined over the following years, were the elegant, long-awaited answer. The number of electron neutrinos arriving from the Sun was indeed only about 1/3 of the theoretical prediction, exactly as Ray Davis had found decades earlier. But when SNO counted the total number of neutrinos of all types, the number matched the Sun's predicted output perfectly. The missing neutrinos were not missing at all. They had simply changed their identity on the 8-minute journey to Earth, morphing into muon and tau neutrinos that earlier experiments were blind to. This decades-long quest, spanning from a tank of cleaning fluid in a South Dakota mine to a sphere of heavy water in a Canadian one, was more than a solution to a single puzzle. It was a triumph of international collaboration and sheer human ingenuity in the face of a particle that treats solid rock like empty space. By proving neutrinos oscillate and have mass, it forced a rewrite of the fundamental standard model of particle physics. But perhaps its greatest legacy is the new window it opened on the cosmos. We now have neutrino astronomy. Detectors like IceCube at the South Pole use the Antarctic ice itself as a medium to catch these ghostly messengers from the most violent events in the universe, from supernova to active black holes. The solar neutrino problem, a whisper of discrepancy that lingered for over 30 years, taught us to see the universe not just with telescopes, but with tanks of water and ice, listening for the faintest ripples in the subatomic sea. Our own galaxy's grand design should have been a fleeting illusion. Look at any image of a majestic spiral like the Milky Way, and you see graceful arms arcing out from a brilliant core, traced by the blue fire of newborn stars and dark lanes of cosmic dust. But this presents a profound mechanical puzzle. Stars in a galaxy do not orbit in lockstep like a rigid wheel. Those closer to the galactic center whip around much faster than those farther out, following the same basic orbital rules as planets in our solar system. If the spiral arms were fixed bands of stars, this differential rotation would tear them apart within a few 100 million years. The arms would wind up tightly, like strands of syrup stirred in coffee, until the galaxy's structure blurred into a featureless disk. Yet we see spiral patterns everywhere in the universe, in galaxies billions of years old. How could these delicate structures possibly persist for generations? This was the winding problem, a paradox that suggested the beautiful spirals we photograph were either very young or we were fundamentally misunderstanding their nature. The solution arrived not from a telescope image, but from a theoretical leap in the 1960s proposed by the astrophysicists C. Lin and Frank Shu. They suggested we were looking at the spiral arms all wrong. The arms are not permanent collections of stars, they are patterns. Think of a traffic jam on a busy circular highway. The jam itself is a region of high density, a pattern of slowed movement that persists for hours, even though the individual cars entering it eventually slow down, crawl through, and then speed up to leave it behind. The jam moves at its own speed, independent of the cars flowing through it. Lin and Shu propose that spiral arms are exactly that, rotating density waves sweeping through the galactic disk. These are regions of slightly stronger gravity, a ripple in the galaxy's gravitational field that moves more slowly than the stars and gas. As a star orbiting the galaxy approaches this gravitational ripple, it gets tugged inward slightly, slowing down and spending more time in the crowded region. Gas clouds also pile up and compress in this wave. This compression is the crucial spark. It triggers the collapse of those giant molecular clouds, igniting bursts of star formation. The brilliant, short-lived blue giant stars that so strikingly outline the spiral arms are born right there in the wave, lighting it up like a neon sign, only to explode as supernova millions of years later, long after they have left the pattern behind. The density wave theory was elegant, but it took decades of patient observation to confirm. Astronomers needed to map not just the light of galaxies, but the precise motions of stars and gas within them. Using radio telescopes to track the velocity of hydrogen gas and sophisticated optical measurements of stellar movements, they could finally see the predicted flow. The data revealed exactly what the theory forecasted: stars and gas streaming into the spiral arm, slowing down within it, and then accelerating out the other side, while the pattern of the arm itself remained stable. This solved the winding problem completely. The spiral arms are not material things that need to survive. They are self-perpetuating gravitational rhythms, cosmic traffic jams that trigger the birth of stars as they slowly revolve, giving galaxies their enduring and majestic shape. The delicate spiral arms of galaxies are local patterns, but the ultimate cosmic blueprint demanded a far grander uniformity. For centuries, a simple, profound idea has guided our study of the cosmos, the cosmological principle. It states that on the very largest scales, the universe is both homogeneous and isotropic. Homogeneous means matter is evenly distributed, like the batter in a well-mixed cake. Isotropic means it looks the same in every direction you look, with no special center or preferred axis. This principle is not just a philosophical preference, it is the essential foundation upon which our entire model of the Big Bang and cosmic expansion is built. Without it, our equations would crumble and our place in the cosmos would become a terrifying anomaly. Yet for decades, this bedrock assumption faced a serious, growing challenge from the maps we were making of the nearby universe. As our telescopes peered deeper, they revealed a cosmos frothing with structure, vast walls of galaxies, immense voids of near-nothingness, and great filaments that stretched across billions of light-years. To the human eye, this looked anything but smooth and even. It appeared lumpy, chaotic, and decidedly anisotropic. Could it be that the cosmological principle was simply wrong? Was the universe, in its grand architecture, fundamentally lopsided? This was not a minor technical dispute, it was a crisis threatening to unmake our understanding of cosmic origins. The only way to settle it was to look beyond the local froth, beyond the galaxies and clusters, to peer back to the universe's earliest childhood. The answer was written in the oldest light there is, the cosmic microwave background. This afterglow is a snapshot of the cosmos when it was a mere 380,000 years old, a time before stars or galaxies had formed. If the cosmological principle held, this light should be almost perfectly smooth, a uniform glow across the entire sky. The first satellite to test this with precision was NASA's Cosmic Background Explorer, or COBE, in the early 1990s. When it released its first full sky map, the result was both stunning and deeply reassuring. The CMB was spectacularly isotropic. The temperature was the same in every direction to an astonishing degree, varying by less than 1 part in 100,000. That is like the surface of a pool being smoothed to within the height of a single human hair. COBE had confirmed the large-scale isotropy of the universe in one magnificent image. But the story did not end there. Those tiny fluctuations, those 1 part in 100,000 ripples, were not imperfections, they were the seeds of destiny. They represented the faint gravitational fingerprints of the first density variations in the primordial soup. Slightly denser regions, seen as slightly warmer spots in the CMB, had a tiny bit more gravity. Over the next 13.8 billion years, that extra pull would slowly draw in more and more matter. Those minuscule wrinkles would grow under the relentless force of gravity, first into clouds of gas, then into the first stars, and eventually into the galaxies, clusters, and colossal filaments we see today. The later, even more detailed maps from the WMAP and Planck satellites confirmed this picture with breathtaking precision. They measured the statistical pattern of those fluctuations, proving they were exactly the kind of random, Gaussian variations predicted by the theory of cosmic inflation, a brief period of hyper-expansion in the universe's first fraction of a second. The resolution to the decades-long mystery was now complete. The apparent anisotropy we see in the galaxy maps today is not a violation of the principle, but its glorious consequence. The universe is smooth and isotropic at its foundation, as proven by the pristine CMB. The magnificent, frothy structures we inhabit are simply the amplified result of those quantum seeds, grown to cosmic scale by time and gravity. We live in the detailed embroidery, but the underlying fabric of the cosmos is, and has always been, profoundly even. These cosmic stories share a powerful and humbling truth. Every single one of them began not with a triumphant answer, but with a stubborn, baffling question. A line on a chart that made no sense, a hiss in a radio antenna that would not go away. A star that vanished and reappeared on a schedule no one could decipher. For years, sometimes for generations, these anomalies stood as glaring contradictions to our best theories, silent reminders of how much we did not know. The journey from confusion to understanding was never a straight line. It demanded the patient, often lonely, work of individuals who refused to let a mystery go unsolved. It required technological leaps, from the first crude radio telescopes to planet-spanning virtual observatories and detectors buried deep underground. And yes, it sometimes relied on a stroke of sheer cosmic luck, like a military satellite finding the wrong explosion, or a graduate student noticing a tiny pulse others might have dismissed. What unites these 30 discoveries is the relentless human drive to make sense of the cosmos, to stare into the abyss of our own ignorance and slowly, painstakingly, bring a little more of it into the light. The puzzles we have solved have utterly reshaped our place in the universe. We now know we orbit a supermassive black hole in an accelerating cosmos, that the atoms in our hands were forged in stellar explosions and neutron star collisions, and that our entire galactic home is adrift in a river of galaxies flowing toward a gravitational continent. These are not just facts in a textbook, they are the pillars of a new cosmic story, one where we are both insignificant and profoundly connected to the grandest processes imaginable. And the most exciting part of this story is that it is far from over. For every mystery we have unraveled, a dozen more whisper from the data. The true nature of dark matter and dark energy, the source of the most powerful fast radio bursts, the precise fate of our accelerating universe, these are the great unsolved chapters waiting for their detectives. The next anomalous signal, the next impossible measurement, is already being recorded somewhere, right now by a telescope or a satellite or a detector quietly humming in the dark. It is waiting for someone to notice, to ask the right question, and to begin the decades-long work of turning a cosmic whisper into a revelation. So stay curious. Look up, wonder at the night sky, not just for its beauty, but for its secrets, because the greatest discovery of all might just be the next one, and the person who helps solve it could be you.